Okay. So the last time we started the best policy identification problem, I will do a recap now of what we did. Today we are gonna try to finish the topic, so we can start with the Bayesian hypothesis testing problem. Um, so in best policy identification, we are simply trying to extend the best arm identification problem to MDPs. Recall from the last time that we have a market decision process, which is a generalization of the bandit model. So we have this MDP, which is affected by the actions that we take. And the action basically will affect the internal state of the MDP. So you take an action, and based on this action, the state will evolve in some way according to a transition function. So you take action AT, and then you will observe how this state evolves, and we denote the next state by ST plus 1. And upon choosing the action AT, you will also observe a reward RT. So formally, we have a definition of state space, which is a collection of states that we assume to be finite. We also have an action space, which is also assumed to be finite for this topic here. And then we have the transition function, which dictates how the state evolves over rounds. We also have the reward, which is function of the current state action pair. And then we define a policy to be a collection of probability kernels, such that based on the data you have observed so far, these kernels define how the next action will be sampled. But for simplicity, we just assume the policy to be a collection of stationary and Markov policies, so that the distribution over time, it's always the same. And the policy pi depends only on the last state and not on the entire history. So here we denote ht minus 1, the entire history up to and including t minus 1. So for this class of policy, we define the value of these policies as the sum of discounted total or discounted rewards. This is also called expected total discounted reward. And gamma here, it's a discount factor that belongs to 0, 1. From this definition, we can define what is the Q value, so the value of taking action A in a certain state, and then follow that policy. And also the definition of optimal policy. So the policy by star that maximizes the value in all states. So these are the basic things that we need. The problem is about identifying the best policy as quickly as possible with a given confidence level. And for this problem, we will also need the definition of suboptimality gap, which is basically the difference in a certain state between the value of V star in S minus the value of taking action A in that state S under the optimal policy. So this is the gap in SA. And this quantifies basically how difficult it is to identify that A is suboptimal. So in particular, the inverse of the suboptimality gap squared will quantify the difficulty of learning that action A is suboptimal in that state. And delta mean quantifies the overall minimum gap strictly bigger than 0 in the MDP. We also make some assumption on the MDP such that it's communicating. The communicating properties only means that between any two states, there is always a policy pi that guarantees you can go from this state S to S prime in a certain number of steps. So basically in a communicating MDP, you can always navigate the MDP. Another important notion is the notion of stationarity. If we define by NTSA the number of times we visited a certain state action pair up to time t, one of the questions we ask in general is this limit NTSA over t, does it exist in the limit? Is it converges to something that is constant, or is it oscillating? In case this quantity converges to a finite quantity, we say that pi induces a stationary distribution. And we call this stationary distribution d pi. So you can think of d pi as the distribution that we approach asymptotically. And d pi basically represents the frequency of times we're going to sample this state action pair. And one can show that this stationary distribution needs to satisfy these the Kolmogorov equations that are also called stationarity equations, which basically says that the time you spend in a certain state S is equal to this sum over all the other state action pairs of the probability of going at state S, given that you were in S prime A prime. So basically, it is a term on the right is quantifying the probability that from any other state, you will go to state S. And you can show that in a Markov chain, you can guarantee the existence of a unique stationary distribution if, for example, the Markov chain is aperiodic and irreducible. So irreducibility means that the policy that you chose basically guarantees that you can visit all the states in the MDP. And aperiodicity, for example, it's needed to avoid oscillations. Because in that case, we cannot work anymore in this setting. We need to kind of take an average. So for simplicity, we just assume that the Markov chain is aperiodic, so we avoid this problem of oscillating between states. So this was just the preamble, but from here we derived a couple of results. So we show that what is the lower bound, and here the lower bound compared to the best arm case, it's a bit different because we need to take into account how we navigate the MDP. So in a bandit model, you can sample any action you want, but here the issue is that you cannot just simply sample any state action you want. You're constrained by the transition function on the sequence of states that you will visit. And because of that, you have some constraints that we call navigation constraints. So these navigation constraints will limit the states that you will visit in the MDP. And we have shown that the sample complexity is lower bounded in this way. So as the confidence error or the false positive rate goes to 0, we have that the sample complexity divided by log 1 over delta, it's lower bounded by T star m, the characteristic time of the MDP. You can think of this as a rate. So the rate of change as delta goes to 0 is lower bounded by T star. And T star represents the characteristic time. And its inverse, it's a sort of evidence ratio or information ratio. And this is given by this optimization problem. We have this supremum over distributions, infimum over alternative models of this quantity. This is the average evidence. The infimum is basically picking a model that is confusing for you. So a model that maximizes the likelihood of having generated that data, but such that the model admits an optimal policy that is different from the optimal policy in the true model. And what you want to do is to compute a distribution W that maximizes the evidence that you can collect. And this W needs to satisfy the navigation constraints, which in the end, asymptotically, because we take the limit, we can show that these navigation constraints simply become the stationarity constraints. So by taking the limit as delta go to 0, we are cheating basically with time, because here delta going to 0 in a sense means that the sample complexity is also tending to infinity, so we're letting t go to infinity. And because of that effect, we are working as stationarity. So we are cheating because we are only considering the problem of exploration as stationarity. We are not considering what happens before. And this is still an open problem, actually. So, okay, we do this. The next problem that we face is the fact that the set of alternatives, so the set of models that maximize, that could have generated this data, it's a non-convex set. So solving this infimum, it's in general a non-convex problem. So what we did in the last lecture is try to find a way to convexify the problem. And what I showed in the last lecture was a way to basically enlarge this set of alternatives, try to find an alternative condition such that we find another set of models that includes also the set of alternatives. By doing so, we found this new condition. The set of alternatives was enlarged, but you want to enlarge it in a way that it's smart. You don't want to do it in a very trivial way. So what we found in the end is that it was a lot of computations. So what we found in the end is that the characteristic time in any distribution W, it's always upper bounded by the sum of two terms. So now I will maybe show the lecture notes for this, since it's a bit more clear. But what we showed is that the characteristic time evaluated in any distribution W, it's upper bounded by this relaxation. And the relaxation here is given by the sum of two terms. So as you can see, in the first term, we have the suboptimality gap squared in state action SA. And then we have this additional term that accounts for the minimal gap. So this result shows how the properties of the MDP come into play and how these properties affect the sample complexity. Here at the numerator, we see this infinity norm of the difference between the value of the optimal policy in the true MDP minus mu SA, where mu SA is the expected value in the next state starting from SA. This is taken in infinity norm, but in the two norm, it's basically the equivalent of the variance of the optimal value. So you can think of this term as some sort of variance. So this is accounting for the aleatoricity, so the randomness that we have in the transition function. And this term here instead is accounting for the fact of understanding that A is suboptimal in state S. We also had a similar structure when we studied best arm identification. So in best arm identification, at the numerator, we had sigma squared, so the noise of the rewards in the Gaussian case, divided by the gap squared. And here it's a similar thing. We have the noise of the transition function divided by the gap squared. We could also have the noise of the rewards, but in this case, we assume deterministic reward. But otherwise, for stochastic reward, we would get an additional term here with the variance of the rewards. So we stopped here the last time. And what we are going to do now in the next half an hour is try to design an algorithm that will take advantage of this result. And we are going to use exactly the same idea that we use for best arm identification. The lower bound, it's already telling you how many samples you need. The lower bound is already telling you that if you minimize this quantity, this is the best you can do. Obviously, this is a relaxation, so maybe there is something better than you. But imagine you could solve the problem in T. So taking the infimum over W of T, this gives you the best sampling policy because this minimizes the characteristic time. And the inverse of the characteristic time is just the average evidence. So your goal is to maximize the evidence. Minimizing W, it's a way to maximize this evidence. So W represents the best, W star, the solution to the optimization problem, represents the best sampling distribution for this. There are also a couple of other properties that we are not gonna prove just for the sake of time. But one can show that the problem here, the minimization over W, it's a convex problem because we are just trying to optimize a function of this kind, C over W, but it's not strictly convex. So in reality, we might have multiple optimal solutions, but for simplicity, we are just going to deal with a single solution case. And we can also show that there are some continuity property for this relaxation, and this will come useful later when you want to prove the sample complexity upper bound. So let me write briefly the ideas here. Okay, so we know that the lower bound in general looks something like this. So the sample complexity is always lower bounded by something that it's the characteristic time times this log 1 over delta, that it's basically the confidence term. And this lower bound is telling you that in general, on average, you need this number of samples to identify the best policy. What we did was to find an upper bound on T where T inverse is defined in this way. So T inverse computed in W, it's simply the inner minimization problem without the optimization in W. So the last result, we showed this, where TW in a certain MDPM is defined in this way. So what we're going to do now is to treat this relaxation as the new characteristic time. So now what we want to do is to find an algorithm that is going to be asymptotically optimal with respect to U, not with respect to T anymore. So we treat U as the new characteristic time. And we define U star in a certain MDPM as simply the infimum over all distribution W that belong to the set of stationary distributions of M of UWM. So the optimal relaxation is the one that solves this optimization problem here. So right now, basically what we are doing is replacing T with U. And the idea, as in track and stop, is, okay, let's just then compute this W and try to explore according to this W. I mean, if this is the best you can do, why just not apply W star and explore according to W star? W star will induce a stationary distribution from which you can extract a policy that we are going to call the oracle policy that we can define in this way. So let me write like this. So W star is a distribution over state action pairs, and you can show that a policy defined in this way induces a stationary distribution W star. But the problem is we don't know M. We don't know the true MDP. So we cannot compute what is the true optimal distribution. So what we're going to do is the same idea as in track and stop, and simply use the empirical estimate of the MDP. So what is the empirical estimate of the MDP in this case? We make the assumption that we know the rewards. So we know the reward function. It's deterministic for simplicity. So the only thing we don't know is the transition function. And we can use the maximum likelihood estimator, but in general, a simpler alternative is just to take a transition function that is proportional to this term here, alpha plus nt as a s prime, where nt as a s prime is the number of times I visited this triplet. And alpha is called the Laplace smoothing. So alpha, it's taken bigger than 0, and usually it's set equal to 1. So in the end, the empirical estimate of the MDP is given by this transition function, this empirical transition, which is simply alpha plus nt as a s prime divided by alpha times the size of s plus sum over, let's write s second of nt as a s second. So in the following, I will write MT to denote the empirical estimate of the NDP, but this is simply PT. In the case we didn't know the rewards because maybe the rewards are stochastic, we would also need an estimate of the reward distribution. So in that case, it's better to just use the notation MT. So I'm gonna stick to MT to indicate the empirical MDP. So based on this empirical MDP, we are gonna compute the optimal exploration for that empirical MDP that we are gonna call WT star. So WT star is the arc inf of all possible stationary distribution for MDP MT. And as in track and stop, we also need to guarantee that we are estimating well the MDP. Because simply applying WT star doesn't guarantee that you will end up estimating well the MDP. Also in track and stop, we had a similar problem. Because if you're gonna use the wrong estimate here, if you're not estimating well the MDP, it might be that the resulting optimal policy, the optimal sampling distribution that you get might be too far, too different from the true W star. So what you want to do is to ensure that asymptotically or at some rate, you are converging to the true MDP. So your estimate will converge to the true M. So if the estimate converges to the true M, then because of continuity, you can show that this WT star will converge to the true W. And this is something we require to show that asymptotically we are exploring in the optimal way. And the simplest thing we can do here is simply to mix this distribution here with a distribution that guarantees that we're going to sample all actions in every state. And because of that, we're going to prove that asymptotically, we are sampling all state actions infinitely often. So what we are going to do now is to define the optimal policy at time t, which is defined similarly to this one. So we're going to define this policy here, which is simply the ratio of W star T in SA divided by the sum over action of WT star SB. So when I write optimal policy, I mean optimal exploration policy, not the optimal policy of the NDP, but just the optimal exploration policy induced by WT star. And what we're going to do is we are going to mix this policy using a mixing coefficient alpha t with another distribution. And we are going to call this convex combination the final exploration policy at time t. So the role of this forcing distribution is to ensure that asymptotically our estimate of the NDP will converge to a true estimate. So that this property will lead to this other property, that our WT star will converge to a true W star. So now the problem becomes, how do we choose this forcing policy? And in this case, we are going to use a different method compared to the one we use in the bandit case. So in the bandit case, we were using a deterministic policy. Probably we can also do something similar here, but the computation will just become more messy. So it's just easier usually to take this convex combination and define this forcing distribution. One, for example, could use as forcing distribution just a uniform distribution. There are also other possible choices. But what I'm going to do now is to show under which conditions we can guarantee that our estimate will converge to a true estimate. So we have this lemma. So fix some state, any state. And we define T as I to be the time step. We visited state S for the IF time. Under the event that we are going to visit this state infinitely often, if this sum here is equal to infinity, then we have that. We have that for any state action pair, we are going to visit those pairs infinitely often. So the idea is that if for any state S you can guarantee that any action will be sampled infinitely often, whatever the state. Then you can also show that every state action pair will be visited infinitely often. And this requires, we will use the property that the MDP is communicating, so that between any two states, you can always find a way to visit, to go from one state to the other. And this FTSI is simply the filtration of data up to the time step you visited state as the IF time. So the proof is quite simple in general. So we start by fixing some state action pair. And we also define the event EI such that we sampled action A. The IF time we visited state S. So now the point is that we are going to use just the Borel-Cantelli lemma. Which says that if I'm not going to use I because maybe it will confuse with the other index. So the Borel-Cantelli lemma tells you that if this is true, then you know that the event En satisfies this equation here. So this equation here is simply telling you that the event that you are considering here will happen infinitely often. So we are gonna simply apply this lemma here. So in case we have this condition, so if we can guarantee that this sum is equal to infinity, then because of this lemma, what we have is that action A will be sampled infinitely often. So whenever we are in state S, we can guarantee that the number of times we sampled action A in that state S will go to infinity. But now the issue is that you want to guarantee that this will happen in any state action, not just in that state. So what we are going to do now is we're going to define S infinity to be the random set of states that are visited infinitely often. And we are trying to gonna reason, and by contradiction, try to see that there is no state that we are not gonna visit, like just a finite number of times. So we define S infinity to be the random set of states that are visited infinitely often. We also let S0 to be any subset of the set of states. And since with the MDP is communicating, we know that there exists S that belongs to S0, S prime that doesn't belong to S0, and an action A such that P of S prime given SA is bigger than 0. So why does this hold? Because the MDP is communicating. So between any two states, so in the MDP, if you split the set of states in any two clusters, you can always find two states, one in one cluster, the other state in the other cluster, such that they are connected. Because if these two clusters are not connected at all for any action, then there is no way this MDP can be communicating. So you can always find S prime and an action A such that this transition inequality holds. So now we're gonna simply look at the probability that S infinity is equal to S0. And here by simply a law of total probability, you can just write S infinity equal to S0, comma, S prime that belongs to S0 plus probability of S infinity being equal to S0, S prime that does not belong to S0. So the first probability is simply equal to 0 because S prime doesn't belong to S0. So now we need to reason that also this probability is equal to 0. And if we manage to show that this probability is also equal to 0, then it means that S0 cannot be just any subset of S. It must be the entire set of states. So here, in reality, it's better if I write S infinity, even though we impose S infinity equal to S0. But it's the same thing. Yes, so we want to show that this other quantity is also equal to 0 if S0 is a strict subset of S. So the idea is we want to exploit the communicating property. So let's take, for example, state S. And we know that state S belongs to S0. So what we're going to show is that we are going to visit S prime infinitely often. So we can define, we can look at this probability. So we are going to try to use again Borel-Cantali to show that S prime will be sampled infinitely often. So to show that, we are going to look at this probability. So sum over I from 1 to infinity, probability that we are going to visit state S prime, the IF time we are in state S. So here you can do law of total probability over the actions. And now what you can simply do is to lower bound this quantity with just one of the actions. you could take the action that we fixed in the beginning, for example, or I mean this action here. So we know that that action admits a transition probability that is strictly bigger than 0. And so this quantity, you can show that it's simply lower bounded by P S prime given SA times the probability, and here we're going to simply use Bayes rule, probability that the IF time with the state S, we picked action A. But this quantity is bigger than 0, and we know also that this sum over I will diverge. So we have just shown that the number of times we visit S prime, it's happening infinitely often. So S prime is happening infinitely often, which means that S prime must belong to S infinity, but then this leads to a contradiction here. Which means that the set S0 must be equal to the entire set of states. Yeah, so for example, let's say we have a uniform policy. Does the uniform policy guarantee that condition? So the condition we want to satisfy is that the probability that we sampled action A, the IF time we are in state S, this sum goes to infinity. So what is the probability that we pick this action, the IF time we are in a state S? So if you are mixing with a uniform policy, so remember, we are choosing actions according to this policy. So let me rewrite it here. So for example, let's say we choose alpha and phi in a certain way. So we're going to choose, for example, alpha t to be equal to 1 over the number of times we visited state S. And then phi t will be simply a uniform distribution. So we can choose alpha t to be equal to 1 over number of times we visited state S. And beta is just some coefficient that you can choose as you want. So we want to show that this holds. So the probability that in any state we pick a certain action A will be simply lower bounded by, so this quantity here will be lower bounded by sum over I, 1 over the size of the action space times NI. So here we should use but this NTI of S is simply equal to I. So this simply becomes 1 over size of the action space, sum over I, 1 over I, and the sum of 1 over N, or 1 over I in this case, it's simply diverging. So the uniform policy guarantees this property. There are also more sophisticated forcing policy that we could use. For example, you could use phi t to be equal to some softmax of the visitation vector. So this policy will select, so we'll put more probability mass on actions that have not been selected as frequently as other actions. So this is usually what I use in my numerical results. But also uniform policy, it's fine, just for the sake of explaining the ideas. So now that we have guaranteed this, well, we have just shown that using the uniform policy allows you to say that the probability that in the limit of t that goes to infinity of NTSA, it's equal to infinity almost surely, so equal to 1. And because of this, we are now able to also show that our MDP estimate will converge to the true MDP almost surely. And because of the continuity property of the relaxed characteristic time, we also have that U of WT star MT will converge to the U star of M asymptotically. Yeah, that's pretty much it. There are some other issues here that we should talk about, but these are rather technical problems. So here the subtlety is that we want, in the end, to ensure that the average number of visits to any state action pair will converge to the true W star. So this is a bit tricky because this is a stationary distribution, but this quantity here, it's not necessarily a stationary distribution. So you are trying to track a stationary distribution over time, and you want to guarantee that asymptotically you're converging to this W star. So this is quite technical, and I will not through the details, but the idea is simply to show that these kind of policy that we use guarantee a certain number of properties, one of which is the fact that we are assigning positive probability mass to over all the actions. So assigning positive probability mass to all the actions is something that will help us with the aperiodicity and the irreducibility. And because of that, then you can show that there exists a unique stationary distribution, even though we are using this kind of time-varying policy. And in the end, you can show that this result here will hold with probability 1. So we can also look at the lecture notes for this. We can just look at this briefly and then we take a break. So the final algorithm is this called navigate and stop. We are computing the WT star at every time step using the empirical MDP that we computed. And from this WT star, so the stationary distribution for MT, we can compute what is the oracle policy for that MDP. Then we are gonna take this convex combination between pi t star and the forcing policy. We compute this new exploration policy. We are gonna sample an action according to this policy. We are gonna observe the next state. And based on the new observation, we update our empirical transition function, and then we continue. We continue until we reach some stopping condition. Before we go to the stopping condition, let me finish with the sampling rule. So in the sampling rule, we are computing first WT star. This is based on the empirical MDP, which is defined in this way, according to this empirical transition. Here we have the additive smoothing alpha that I usually choose to be 1. And then we can choose the alpha t, the mixing coefficient, to be 1 over NTS to the power of some coefficient. So here, this is a hyperparameter that you can choose how to tune. So in the proof, it didn't have much effect, but here in the lecture notes, I also choose a different forcing policy than the uniform. And if you choose a different forcing policy, then you need to tune this alpha. You can also check the lecture notes for more details. And yes, with this sampling rule, you can guarantee that all state action will be visited infinitely often. So you are estimating the NDP very well. And to guarantee that the average visitation also converges to W star, we need to use some results about ergodicity. And the result that we're going to use is this result from this paper from Fort, 2011, which says that if you guarantee these 5 properties, then you can show that the average visitation will converge to a stationary distribution. So these properties that we need to guarantee are simply properties that basically we are inducing an aperiodic and irreducible Markov chain at every time step. So once we have that, this result that the average selection frequency will converge to W star comes almost naturally. This holds almost surely. And this is basically all we need for the sampling rule. For the stopping rule, the idea is the same as in track and stop. We need to follow the lower bound, right? So the lower bound is telling you that you should sample this number of samples. But we don't know the model. So we need to account for the model. We need to pay an additional price that is usually log t. If you remember, in track and stop, we had the threshold rule that was log 1 over delta plus a logarithmic term in t. So we have something similar here, and we can show a similar threshold rule also in this case. So the threshold rule that we can prove, it's given in equation 5.3. So the structure is very similar to the one we had in the bandit case. We have log 1 over delta plus basically the number of states minus 1, sum over state actions of the logarithm of a quantity that depends on the number of visits to state S and action A. And that's it. Once we have all these ingredients, the proof of proving the sample complexity upper bound, it's exactly the same as in the bandit case. And we can show that in the limit, as delta goes to 0, the sample complexity divided by log 1 over delta, it's upper bounded by U star of M. So asymptotically, we are exploring in the optimal way according to you. So yeah, let's maybe take 10 minutes break, and then we're gonna start with the Bayesian stuff. Okay, so let's continue. And I think we managed to survive the heaviest part of the course so far, like the most theoretical intensive. So from now on, we will just look at the case where we have like a Bayesian prior over models. So we're gonna cover what I call the Bayesian pure exploration case. So in this case, we are going back to the first lecture. So in the first lecture, if you remember, we were looking at two different problems, the fixed budget, the fixed confidence. So in the fixed budget, we wanted to solve this kind of problem. And let me repeat what every symbol means. Um, so in the fixed budget, we have basically theta, which is a parameter of the underlying model. We have this star theta that represents the true hypothesis. It belongs to some space capital D. Then we have at D, that is function of the trajectory up to capital N steps. So D hat, it's a mapping from trajectories to decisions. This is also called the inference rule. And then we have pi. Pi is a sampling rule. It's a collection of policies where each policy is a probability kernel over actions. So let me define also what is a capital H to be precise. So because we will need it. So we define capital H n to be the sequence of observations and actions that we took. So starting from 1, so we have first observation, x1. So I don't use the notion of state anymore. Now I write observations. So observation x, the first one is x1. Then we have some action that we took, a1, and so on, up to xn minus 1, an minus 1, xn. So this belongs to the set of trajectories that is defined in this way. So we define this calligraphic X to be the set of observation, capital A to be the set of actions. So we are taking this Cartesian product between X and A, and then we do this product n minus 1 times, and then we do an additional Cartesian product with a set of observations, and this represents the entire set of trajectories up to time n. So, and the actions in each round is sampled from this probability kernel that is a function of the history up to that time step. So this is a probability kernel over the action space. And maybe let me write it calligraphic A so we don't confuse with this A here. Okay. So this is all the notation we need, I think. So we are taking a supremum over the possible inference rules, the possible sampling rules. Supremum of what? Of the probability that under this sampling rule for this fixed model, we are going to infer the true hypothesis at the final time step. So this is what we discussed at the very beginning of the course. But this was for a fixed theta, so a fixed model. So what we're going to do now is try to introduce a prior over models. So let's say we have a prior Q over the set of models big theta. So this is the set of possible parameters. And remember that theta, it's parameterizing the observations. So the distribution of the observations. P theta. Where P theta here, so we know that the observation at time step t is sampled from this distribution here. So this is simply equivalent to P theta sampled from ht minus 1, comma at minus 1. We are also gonna omit the dependency on the time step from P for simplicity, but it's there because the distribution is different at each time step. In general, in the bandit case, it is not, but in some other problems, it is. So basically, we understand that a single parameter theta induces basically a model P theta. And so we can define the set of possible models. It also induces the true distribution, the true hypothesis. So we can define the set of models as simply these tuples. For any theta that belongs to the set big theta. So there are a couple of boring definitions that we need, but I'm not gonna go over the details for this. So we need to define what are the probability measures here that are involved in this problem. So we define the prior Q over theta. We defined also what is the set of possible models. So the set of possible models is given by the variation of theta that belongs to big theta of this tuple that is function of theta. So we could also call this tuple simply phi of theta. So now the problem is try to define the probability measures over the trajectory space and also defining the posterior distribution and so on, because we are working the Bayesian case now. So it's not the frequentist case anymore. This is a measure difference. And a reason why also we want to move to the Bayesian case is that some of the computations become a bit easier. The definition of optimal sampling rule, it's also easier to define and to also be computed using techniques from deep learning or RL. So we can define, for example, the probability of a certain trajectory at time t under sampling rule pi for a fixed model. So here A is any set of the Borel sigma algebra of trajectories. We're gonna define the space of trajectories at time t to be zt. So zt here, it's what I wrote before. It's this Cartesian product. And this ht is the trajectory up to time step t. So what is this gonna be? We can use this definition here. And I think it's just better if we also indicate the time step, because otherwise it will be confusing. But let me do it without time step for now. So what is this gonna be? Remember that ht is the trajectory. So x1, a1, x2, a2, and so on. A, we can think, since this is the Borel sigma algebra of cylinders, we can just simply consider any A of this form. Where each Ci belongs to the set of observation and Bi belongs to the sigma algebra of the set of observation. We are going to use the Borel sigma algebra. And Bi belongs to the Borel sigma algebra of the action space. So we can always consider any subset of this set as the Cartesian product of these sets Ci, Bi. So in the end, this product, this probability measure can be defined using the Ionescu-Tulcea theorem in this way. So this will be simply integral over C1 of p theta, the x1, integral over b1 of probability that the first policy took action a1 given x1, and so on. And you can keep going in this recursive way. So this is simply the probability of a trajectory. This is the way we define the probability measure over trajectories for a fixed model. And from this definition, we can also define what is the joint probability between trajectories and models. So the joint at time t, I'm just gonna write it in this differential way without writing the integrals. It's simply gonna be this measure here. So probability measure of theta, t pi, the ht. This is a probability kernel for a fixed theta times the prior distribution over theta. So this is simply saying that the probability measure time step t under sampling rule pi So the probability that ht belongs to some a and theta belongs to some m, it's equal to integral over m probability measure of theta t pi of ht belonging to a integrated over q d theta. So this is the overall joint probability measure of the problem. And from here, if we, well, A is the same A that we took before, and here M is simply any set that belongs to the Borel sigma algebra of big theta. So now if we choose M to be equal to big theta, then what we obtain is the marginal distribution over trajectories. So now the natural question is, we have found the marginal distribution over trajectories. We can also define a probability kernel of the likelihood of a trajectory given a certain parameter theta. Or I should say, we have found the probability kernel of the trajectories for a given parameter theta. Can we do the opposite? Can we find the probability kernels over models given a certain trajectory? So can we find the posterior over models for a given trajectory? So this is the one of the main issues to show that this exists, and to show that we can find this posterior distribution and that we can use it in a meaningful way, we need to make an assumption. So the first assumption that we make is an assumption of domination. So basically, we are going to assume that there exists some probability measure, lambda, over the set of observations, such that for any t from 1 to n, for any trajectory so how did I call this set of trajectory? I think I called it zt. For any actions a, we have that p theta in h a, it's dominated by lambda. And this holds for all the parameters theta. So under this assumption of domination, what happens is that we can define what is the likelihood ratio. So if you know what is the sampling rule, what happens is that the likelihood ratio will be for a given trajectory, capital HT, and a given parameter theta will be simply defined by the Radon-Nikodym derivative here. So let me write it down. So the Radon-Nikodym derivative we are simply gonna call it here f of ft of x given ha semicolon theta. So the absolute continuity implies that this Radon-Nikodym derivative exists, and we are simply gonna call this Radon-Nikodym derivative to be equal to f. So here it's just a definition. And because of that, you can show that the likelihood ratio of a given trajectory in theta, it's simply given by the product of these terms. So we have f1 of x1 theta product from s equal to 2 up to time t of f of s, x of s given h s minus 1 a, and here we have a of s semicolon theta. So I will not go through the details, but because this log likelihood ratio exists, then you can also show that the posterior distribution exists. We have a posterior distribution over models. And we are gonna call it RT. So RT that theta belongs to some set M given some trajectory HT. So this is the posterior distribution over thetas for a given trajectories. So this posterior distribution from this assumption, we can show that it exists. It exists for every time step t. And now from this distribution, we can also define what is the posterior distribution over the true hypothesis. So probability that the true hypothesis belongs to some subset B given a trajectory capital HT, where B it's any set in the Borel sigma algebra of the decision space. So this probability that the star theta will belong to this set will simply be RT evaluated over all the models such that the true hypothesis in that models belong to B. So by defining the log likelihood ratio, we are able to define the posterior distribution over models for a given trajectory. And from this posterior distribution, we are then able to also define the posterior distribution over the true hypothesis, which is simply the measure of all the possible thetas that have as true hypothesis, a true hypothesis that belongs to this set B, where B is any set in this Borel sigma algebra. So now we are just gonna show the last result of today. And the result is simply that the best inference rule is the inference rule that maximizes the posterior distribution. So for any sampling rule pi, for any time step t from 1 to capital N, the budget, we have that the supremum over d hat t of the probability that our recommendation is equal to d star theta. So this supremum is solved by d hat t of ht being equal to max, argmax over hypothesis of the posterior distribution that we defined before, this one. So what this lemma is telling us is that for any sampling rule, so no matter how you sample the data, for any time step, the inference rule that maximizes the probability of correctness at any time step is simply an inference rule that maps the history of data to the maximum over the posterior of the true hypothesis. And here the argmax might have multiple solutions. In case we have multiple solutions, we introduce some ordering to break the ties. And the proof is quite simple. So the proof is simply based on rewriting basically the objective here. So what is this probability here? So so the idea is that first we want to integrate over all the possible trajectories. So here we're gonna have an integral over all possible trajectories of the probability of observing that trajectory under pi of the sum over decisions indicator function that d hat t for that ht is equal to d times the probability that d star theta is equal to d given ht. So we use the results from before. We use the fact that we can derive this posterior distribution, and very importantly, this posterior distribution doesn't depend on pi. So this is something we can show. So we start from here. Basically, we can integrate over the trajectories and applies essentially Bayes rule to show that we have an integral over trajectories of this posterior distribution. And we also use the fact that the decision space in our case is finite. So here we took a sum over d, indicator function that the inference rule is going to be equal to d. So here it's just a rewriting, but let me rewrite it in a better way so it's more clear. So here we have the posterior, and here we have the probability of DHT. So this is always upper bounded by the max over T of this quantity. So if you choose basically dt hat ht to be equal to the argmax of the posterior, so if we choose dt hat ht to be equal the argmax over d of the posterior, then we have just shown that this is also equal to integral over zt. So maybe let's not use the hat here, but let's use another symbols, tilde. So this quantity here is simply equal to probability over t. So probability measure time t of the posterior. So d at d star theta is equal to d tilde ht. This is a measurable function given ht. So we don't have any issue. So this quantity here maximizes the original objective that we wanted, but we can simply attain this objective by simply choosing an inference rule that selects always the maximum. So this is very trivial, but it shows that the optimal inference rule is the one that maximizes the posterior distribution. Yeah, so we're gonna conclude here for today. And tomorrow we are simply gonna show that using a certain reward function based on the posterior, we can train a Q function and show what is the optimal sampling rule for solving this problem. So again, thank you for attending.